So good evening, Leeds, both in Leeds and in Zoomland. This is rocket science, or maybe it's not rocket science, but the idea is rocket science is thought to be hard, but maybe it's not quite so hard if you somehow manage to skip all the maths. So let's just remind ourselves where we are.
What do you do?
Well, I don't mean to boast, but I'm a brain surgeon.
Brain surgery? Not exactly rocket science, is it?
So I'm talking about rocket science. I'm not talking about rocket engineering or rocket technology. I'm not talking about how it is that you build yourself a Saturn V, for instance. It's more about how you get from A to B in the solar system, how you use rockets to get around. So I'll be talking about what a rocket does. I'll be thinking about orbits, both the various shapes and sizes of orbits in the solar system in particular, and then how we get from one planet to another, of course, generally starting from the Earth, and I'll be looking at how we get to Mars and how we get to other planets in the solar system. And then I'll finish in the last section looking at Lagrange points. What are these mysterious parking places where we can park spacecraft? So let's look at the first one first. Rocket science. What does a rocket actually do? If you ask people what is the primary function of a rocket, you'll get a number of different answers, but a lot of them will be, well, a rocket goes up, so its main job is to lift things above the atmosphere. Well, yeah, sort of, but not quite. If you think about the International Space Station and the Hubble Space Telescope, they are actually still inside the Earth's atmosphere. It's just rather thin up there at an altitude of 400, 500, 600 kilometers. If you want to put an object into Earth orbit, what matters is not how high you go, it's the horizontal speed that you can impart to an object that determines whether or not it'll be in orbit. So yes, it's a good idea if you get above as much of the atmosphere as possible, because that will then reduce atmospheric drag and it makes life easier. But strictly speaking, it's not necessary. Newton realized this many years ago. Back in 1686, when he published in his Principia, he showed this picture, original in the top left and expanded in a cartoon version in the main image there. If you put a cannon on top of a mountain and shoot the cannonball sideways, well, the amount of velocity, the speed you need to give that cannonball, will determine its motion. And the idea that it's the horizontal motion, not up or down, that matters is something that we should always remember. If you don't give the object enough speed, it'll simply drop according to the trajectory shown as A. If it goes too slowly, it'll simply fall to Earth. If you shoot the cannonball horizontally faster, it'll go a bit further. It may get as far as B. But if you go fast enough, you can go all the way around the Earth, i.e. you can go into orbit. And Newton also realized that the stronger the gravity, the quicker it'll come down, in other words, the shorter the distance A and B, and hence, for a stronger gravity, the faster you'll need to fire your cannonball in order to go into orbit around the gravitating body that we're talking about. So although we're thinking generally of Earth, it would apply to any body, whether it be a planet or even a star. So this idea of horizontal velocity is not a new idea. So yes, rockets like the Saturn V do initially take off vertically, but it's not long before they start to tilt over. So this is not an optical illusion caused by the camera angle. It is genuinely tilting over, because what the Saturn V is designed to do is to give the spacecraft a significant horizontal velocity in order to get it into Earth orbit. Yes, it lifts it a few hundred kilometers above the surface, but it's the horizontal speed that really counts. If you don't get the horizontal speed right, effectively if you have a spacecraft such as the Blue Origin New Shepard, if you simply go vertically up, then once you kill the engines, you will come vertically down again. And that's precisely what happened. It gets to an altitude of perhaps 100 kilometers or so it gets you technically into space, but you come straight back down because you haven't got horizontal velocity to put you into orbit. And so you end up with a flight time of 10 minutes, you gain altitude, but then you lose altitude. And generally speaking, that's not so good for getting around. So let's have a think about orbits, the various shapes of orbits that exist, especially for planets in our solar system. An orbit is the path of an object affected by gravity, strictly affected by only gravity rather than being pushed around by something else. So we're all used to the idea of planets in orbit around the sun and moons in orbit around their planets. Strictly speaking, an orbit doesn't have to be a closed shape of any kind, and we'll look at non-closed shapes a little later in the talk. But Kepler observed the motions of planets and realized that the planets went round the sun in ellipses, and then later Newton figured out why. His law of universal gravitation explained why all objects move in ellipses or possibly circles, which is only a special case of an elliptical orbit. So Newton realized that by analyzing the mathematics of what was going on, the motion of planets and other objects in our solar system are one of these so-called conic sections. If you take a three-dimensional cone and slice through it, depending on how you take the slice, you will end up with a section which describes how planets move. If you take a slice horizontally through a cone, you'll get a circle. If you slice at an angle, you'll get an ellipse. If you slice at an angle which is precisely parallel to the sides of the cone, you'll get a parabola. And if you slice at a larger angle, something closer to vertical, you'll get a hyperbola. And all of these shapes, circles, ellipses, parabola, hyperbole, these curves that describe the orbits of objects going around a star like the sun, for instance, they're also the same curves that define the shapes of mirrors that can be used to focus light. And the reason for that is because the maths is essentially the same for both. So it might be that we use hyperbolic or parabolic or elliptical mirrors, generally not circular these days, but certainly one of those conic sections will be used to shape the mirrors if you have a reflecting telescope. Now we know that planets follow closed elliptical orbits, so a circle is just a special case of that, but most of the orbits of planets in the solar system will be ellipses, and a couple of them are shown here of different so-called eccentricities, different elongation of the ellipse. If an object falls in from the Oort cloud a long way from the sun, then it will follow essentially a parabolic trajectory shown by the red line at the top there. So something falling in from the Oort cloud starts with almost zero velocity and then falls into the solar system. If an object comes into our solar system from outside the influence of the sun, if it enters the solar system at speed, then it will follow a hyperbolic orbit. And there's hyperbola, which is in a sense a slightly flattened version of a parabola, if you want to think of it that way. We have actually seen some objects come into the solar system. For instance, in 2017, the object called this rock came into the solar system in 2017, and it was coming in at speed and was tracked as indicated by these dates here in July, August, September, October of 2017, and the speed at which it was coming through the solar system made it clear that it must have entered the solar system with a finite speed. Hence it didn't simply fall in from the Oort cloud, and as a consequence it will also be leaving our solar system at essentially the same speed as well. Now, what matters in thinking about orbits and how we get between orbits, and ultimately what matters when we're thinking about Lagrange points, is this basic idea that the strength of gravity will determine how fast objects are orbiting. So let's just imagine a hypothetical situation. We have a planet indicated in green and a planet indicated in red. The green planet is closer to the sun, so it feels a stronger gravitational pull from the sun. And because the gravitational pull is stronger, the planet moves faster and its year is relatively short. By comparison, the red planet is further from the sun, so the gravitational pull of the sun is weaker, and hence the planet moved more slowly to stay in orbit. Remember the cannonball that Newton told us about? If the gravity is strong, you need to fire the cannonball with a greater speed in order to achieve orbit. Now, although these aren't cannonballs, exactly the same thing applies. The green planet experiences a strong gravitational pull, and as a consequence it moves faster than the red planet at a greater distance from the Sun, which feels a weaker gravitational pull. So its speed is lower, and as a consequence it's going through a larger orbit with a lower speed. It takes a lot longer to go around the Sun, so its period, or its year if you prefer, is much longer. That basic idea is central to pretty much everything that I'm talking about this evening, and we'll come back to this again. If we look at the consequence in terms of what's going on around the Earth, this is a very busy slide, so we don't have to worry about all the detail. But if we look at satellites that are very close to the Earth, they take about 90 minutes to go around the Earth, like the space station. Satellites that are further out, like GPS satellites, will take 12 hours to go around the Earth. And geostationary satellites out here where the cursor is pointing, they will take 1 day to go around the Earth, and hence they will be synchronous with the rotation of the Earth. So this idea, the further they are from the Earth, the longer they take to go round, the slower they're moving. Objects around Earth behaving just like objects around the Sun. So Newton figured out the details in the 17th century, and he managed to set up, we're not going to deal with the maths, but he managed to set up the equations and solve them that showed us that the distance of an object to the Sun, indicated by the horizontal scale here, and these units are astronomical units, units of the Earth-Sun distance, those distances are related to the length of time it will take a planet to go around the Sun. And here we've got the period indicated as t, and we're using Earth years as the reference, so 1 equals Earth years. And you can see that all the planets line up perfectly. They know exactly how fast they should be moving in order to go around the Sun. So although Newton figured this out in the 17th century, the planets have known this all along and have been following these orbits with these periods for who knows how many millions or perhaps billions of years. Let's just have a quick look at what happens if we have two objects, one orbiting the other, not necessarily the Earth and the Sun. If we have two objects of the same mass, then they will orbit around their centre of gravity, or as physicists tend to call it, the centre of mass, indicated by that cross in the middle. If the two objects are not the same mass, then they will still orbit their centre of mass, but the larger mass will move a smaller distance, as indicated by that little cartoon. And if we take it a little further, a much bigger mass and a smaller mass, it's possible that the centre of mass might actually lie within the larger object. And if we take that to extreme, it is possible for a very small object like a planet to make a very large object like a star wobble, because the centre of mass, again, is not quite at the centre of the star, and so the star wobbles as it moves around its centre of mass. And this is precisely how some exoplanets have been discovered. Even if we can't see the exoplanet, the fact that the star is wobbling because of the motion of these two objects around their centre of mass, the star is moving, and hence we can use spectroscopy to look at the various emission or absorption lines from the star and see them change according to the Doppler shift. If the object's moving away, they're shifted towards the red. If the object is moving towards us, they're shifted towards the blue. So if the star is wobbling, we see this change in the spectra of the star, and therefore we can tell how much it's moving and deduce the existence of exoplanets. Now, this works fine if we've got two objects. If we want to know how one object orbits around another, regardless of whether they're similar masses or very different masses, we can do that with no great difficulty. Newton told us how to do that. But it's a bit embarrassing to admit the fact that it's a real problem if we have three bodies. So two is fine, but if we have three bodies in motion, it's actually very difficult to solve the equations. If we look at these three objects, they appear to be behaving very sensibly, and they seem to be in three elliptical orbits, but if we watch them, we realise they're not. They're actually, again, gravitationally, they are attracted to each other, but trying to work out what they're doing and what they're going to do next is a very intractable problem. In other words, there are a possible set of solutions for a very few limited sets of circumstances where we can calculate what three objects would do. But in general, for any three arbitrary objects, we cannot find analytic solutions. The best we can do is to get a simulation to tell us what is likely to happen if we run a numerical simulation of the system. So let's think about how we can use our knowledge of orbits to get us from one point to another. So here's, for instance, a little animation of how we got from Earth to Mars. This is the InSight probe launched in 2018. You can see it's launched from the bottom right there. The Earth is blue, the spacecraft is pink, and it's on its way to Mars. Notice that we don't necessarily launch when Mars is closest to Earth. It actually arrives at Mars when Mars is actually about as far away from Earth as it is possible to be. The other thing to note on this particular trajectory is that as the spacecraft itself starts to approach Mars, the spacecraft is actually slightly ahead of Mars and Mars is catching it up. In other words, Mars is actually travelling slightly faster than the spacecraft when the two actually rendezvous. And that's important when it comes to deciding how it is that we're going to get to Mars and how we actually go into Mars orbit. So this is the so-called Hohmann transfer. This is the most energy efficient way of getting from one orbit to another. Let's just dim those colours down a bit because they're a little bit distracting. So let's imagine that we're in an orbit. Earth is in orbit around the Sun in the middle there, and we're trying to get to Mars. The most efficient way of getting there is to leave Earth at one point in its orbit and arrive when Mars is directly opposite where the Earth was. In other words, on the other side of the solar system, on the other side of the Sun. It seems like that might at first sight be rather inefficient, but in fact that's the easiest way to get there. The path we actually take is indicated by this blue ellipse. Let me just temporarily take the other two orbits away. So you can see it's an ellipse. It's an orbit that goes around the Sun, where the closest to the Sun corresponds to the Earth-Sun distance, and the greatest distance from the Sun corresponds to the Mars-Sun distance. So the elliptical orbit just touches the orbit of Mars and just touches the orbit of the Earth. So if we want to leave the Earth and get into that blue orbit, we need to give the spacecraft a bit of a kick. It needs to go faster than the Earth is going. So this so-called Hohmann transfer, we need to kick the spacecraft. We need to somehow boost the spacecraft speed, a so-called delta V, a change in its velocity, an acceleration. So we need to fire a rocket engine of some kind. It doesn't really matter what kind. That's rocket technology, not rocket science. So we increase the speed of the craft and it ends up on the blue curve. And when we get to Mars, remember what we saw in the previous animation, when we arrive at Mars, Mars is actually travelling faster than the spacecraft is. So if we want to rendezvous with Mars, we have to give it another kick to accelerate it up to the speed at which Mars is moving. So we need a change in velocity to get out of Earth orbit, and we need a change in velocity to get into Mars orbit. So we need to burn rocket fuel both when we leave and when we arrive. If we don't fire the rockets when we get to Mars, what's going to happen? If we decide we don't want to land on Mars and we don't increase our speed, then when we arrive at Mars, we find that if we don't give it a kick, we simply fall back towards the Sun on the remainder of the blue curve. The Hohmann transfer, if you like, works backwards. And then we come back to the distance at which the Earth is from the Sun. You might say that's a great idea because if we decide not to land on Mars, we simply come home again. Well, actually, no, because Earth takes about a year to go round the Sun. Well, okay, strictly exactly a year. Mars takes about 2 years to go round the Sun. And if we were to follow the blue ellipse, the Hohmann transfer takes somewhere in between, about 1.5 years. Which means if we leave Earth and decide not to land on Mars and then come back to Earth orbit, we'll come back to Earth orbit 1.5 years later. And of course, that means the Earth will have done one orbit of the Sun and a half an orbit, which means the Earth won't be there anymore. The Earth will now be here, roughly speaking, 1.5 years later. So our spacecraft will come back to Earth orbit, but Earth won't be there anymore. This is one of the problems with getting to Mars. You can only transfer efficiently from Earth to Mars at certain times when Earth and Mars are in the right place, and coming home you have to wait until Mars and Earth are in the right place. That's why a Mars mission takes more than just a few months. It could take years because you have to wait for the right planetary alignment. It's not like going to the moon and back in essentially a matter of days. What about getting to other planets in the solar system? Well, in the 1960s, it was realized that if you can fly a spacecraft close to a planet, you can effectively slingshot past it and get an increase in velocity. And if you can do that, then that means you can explore the outer solar system faster and cheaper by effectively picking up extra speed by flying past some of the planets. In effect, you're robbing the planet of some of its momentum. It's the closest thing you can get to a free lunch in orbital mechanics. You slow the planet down very slightly, but in exchange, you speed up your spacecraft. So how does a slingshot work? How does a so-called gravity assist work? Let's take an analogy of a ball rolling down a hill. So we have a ball sitting on top of a hill and we give it a nudge and it rolls downhill. And of course, as it rolls downhill, it picks up speed. Let's ignore friction, let's ignore air resistance, and just think about what would happen to that ball. It continues to accelerate as it goes further and further down the slope. And then it would reach a maximum speed in the valley of this particular hill-valley system. And then it would slow down as it climbs up the hill on the other side. And if the hill on the other side was the same height, it would eventually get back to the same height again. But whatever increase in velocity we gain on going downhill, we will lose on going uphill. It's a very precise trade-off. In fact, if we were to look at the object at the same height on the downhill part and the uphill part, at the same height, the object would have the same speed. And perhaps surprisingly, it doesn't even matter if the two hills are different height. It doesn't even matter if the two hills are the same shape. I've drawn it as a nice smooth curve here, but strictly speaking, it doesn't matter what the curve is. At the same height, the amount of speed you've gained on the way down will be lost when you reach the same height on the other side on the way up. So you can never win. So in which case, how can you win when it comes to doing a gravity assist or a slingshot past a planet? Well, let's look at that situation. We're going to fly past with maximum speed as we get closest to Jupiter. So that's the maximum flyby speed when we are at our closest to the planet. And we can imagine coming in with some inward speed, and we will increase speed until we reach the maximum flyby speed, but then it will decrease as we come away from Jupiter on the outward leg of our flyby. And we've just said that when we're looking at the effect of gravity, what we gain on the way in, we lose on the way out. So how does that help us at all? Here's the clever bit. The inward speed matching the outward speed is the speed as seen by the object that's producing the gravitation, the gravitational well. In other words, it's the inward speed and the outward speed are the same as seen by Jupiter. But Jupiter itself is moving, it's going around the sun. So if we can arrange it, if we get the geometry right, if we come in towards Jupiter, perpendicular to the way it's moving, but if we can arrange it so that we leave the vicinity of Jupiter, moving in the same direction that Jupiter is orbiting the sun, then that outward speed is relative to Jupiter, and Jupiter effectively gives us a push. We get an outward speed relative to Jupiter, which is heading in the direction we want to go. So we end up with speeds relative to Jupiter that are the same, but if we calculate the speed relative to something else like Earth or Sun or something else in the solar system, we find we can get a considerable increase in speed. For instance, we might approach Jupiter at a speed of something like 10 kilometers per second relative to the Sun, but we might leave Jupiter at a speed of some 25 kilometers a second relative to the Sun. So that can make an enormous difference as long as we get the geometry right and decide how we're going to approach Jupiter and how we're going to leave Jupiter. So it takes a little bit of calculating, but you can see the benefit in terms of the speed increase that we're able to get. So let's see how that's been used with a couple more animations. Pioneer 10, back in the early 70s, left the Earth and headed towards Jupiter to take some images of Jupiter. And as it went by, it did a gravity assist. Notice the pink line, a very abrupt change in direction, ending up heading off in the same direction that Jupiter was moving, and a significant increase in speed. If you watch the interaction again and the flyby, the pink is arriving at Jupiter, the green, and then bam, an abrupt change in speed and an abrupt change in direction. That gravity assist that we were just looking at. So that was done in the early 70s, and Pioneer 11 did something similar. In this case, it used a gravity assist from Jupiter in order to get to Saturn. But notice that Jupiter and Saturn are actually on opposite sides of the solar system. There's a gravity assist from Jupiter. Notice a kick, it's almost a left-hand turn at Jupiter. And then the spacecraft is flung across the solar system until it reaches Saturn on the other side. And then again, it happens to pass Saturn so closely, it effectively gives it another kick. So there we go, a gravity assist from Jupiter. The little tick marks just show you that the actual trajectory of the spacecraft is slightly above the plane of the ecliptic. So it's given a kick and then it arrives at Saturn some years later and passes Saturn and is going fast enough now to leave the solar system. That same trick was carried out later with the Voyager space probes, both launched in the late 70s in 1977, just a few weeks apart. Voyager 1 was launched and had a gravity assist from Jupiter to give it enough speed to reach Saturn, and its main aim when arriving at Saturn was to get a close view of the planet but also the moon Titan. And you notice that as it passes Saturn, no sign of a gravity assist, no big kink, no big change in velocity. So here the aim was not to get a gravity assist from Saturn, so yes, we get a kick from Jupiter, that sends us off towards Saturn, but the aim here is to get a close-up of Titan. Titan wasn't in the right place to give a particularly good flyby of Saturn, so they sacrificed the gravity assist of Saturn in order to get close to Titan. Voyager 1 was successful. Hot on its heels, a few months behind it, was Voyager 2. So by the time Voyager 2 got close to Saturn, it knew that Voyager 1 had already done its job and got pictures of Titan. So Voyager 2 was then free to have a gravity assist from Saturn and send it further into the solar system. So Voyager 2, a flyby of Jupiter and then Saturn, sending it on to Uranus and then Neptune, which just happened to be lined up in the right part of the solar system. Note again, there's no obvious sign of a gravity assist at Neptune itself. The pink line appears to be almost a straight line. Let's just run the simulation again. A kick from Jupiter, a kick from Saturn, sending us into the outer solar system, another kick from Uranus. But when it came to Neptune, they wanted the spacecraft to go over the north pole of Neptune to get a good look at the planet. They weren't worried about optimizing a gravity assist. It was already going fast enough to leave the solar system, basically one of the fastest spacecraft in terms of its velocity relative to the Sun. Again, the tick marks on the left-hand side simply indicate that the actual trajectory of Voyager 2 was actually below the plane of the ecliptic. It went over the north pole of Neptune and got a kick downwards, not a kick in terms of an increase in speed, but a kick downwards. Not only did it not increase its speed, it actually dropped its speed slightly after going past Neptune. We can actually see that if we plot out the speed relative to the Sun as a function of how far Voyager 2 was from the Sun. So when it left Earth, it was going quite fast, but as it moves out towards Jupiter, it loses speed, but then gets a kick from Jupiter, another kick from Saturn, and then a third kick from Uranus. And then notice that the kick from Neptune, as it approached Neptune, it started going faster, but as it left Neptune, it dropped its speed and it ended up going actually slightly slower than when it first arrived at Neptune. Well, that's because they weren't using Neptune as a gravity assist. They simply wanted to fly over the North Pole of Neptune, and if that lost them speed, that's no big deal. They were going to leave the solar system anyway. If you plot out what speed do you need at any given distance from the sun, what speed do you need in order to leave the solar system, the escape velocity, that turns out to be this blue curve. So you can see that as Earth approached Jupiter, it was going more slowly than the escape velocity from the solar system. But by using the gravity assist from Jupiter, that put the red line above the blue line, and regardless of any kicks that it got later from Saturn or Uranus, or a little bit of a slowdown from Neptune, the red line from that point onwards stayed above the blue line, so this object was going to leave the solar system, simply from the kick it got from Jupiter. Jupiter is such a massive planet, then you get the largest gravity assist from flying past that planet. Gravity assist to cover these enormous distances in the outer solar system usually sounds like a very sensible idea. But what is not so obvious is the fact that gravity assists are also used for the inner planets. If you get the geometry right, you can lose speed in much the same way as if you get the geometry right, you can gain speed. And Bepi Colombo, on its way to Mercury, actually went past the Earth and then went past Venus, actually twice, in order to get a gravity assist, not to speed it up, but to slow it down. Otherwise, falling into the inner solar system, the spacecraft would be moving way too fast. So although Bepi Colombo actually encountered Mercury in 2021, it's not actually going to go into orbit of Mercury until 2025. It's going to take 4 years simply to keep passing Mercury. Each time it passes Mercury, it's going to get a gravity assist, which will slow it down to the point where it will then be able to go into orbit. It's far more efficient to use gravity assists either to gain speed or to lose speed. It's much more efficient to do that than it is to actually burn fuel in a rocket motor. If you want to actually fire a rocket engine to change your velocity, well, you can do that, but you have to take fuel with you to do it. And for a lot of these missions, they would rather use the mass available for instruments rather than for fuel to speed them up or slow them down, because the gravity assists effectively are a free lunch. Now, if you are going to change your orbit, yes, you need fuel. So, for instance, Cassini, on arriving at Saturn, wanted to go into various orbits around Saturn because it wanted to image various parts of the surface of Saturn and the rings and the various moons. So when Cassini arrived at Saturn, it did indeed want to change its orbit multiple times, and that does require fuel. You can see the actual structure of its orbits are extremely complex, and it spent many years changing its orbit in order to give it flybys of the planet or the rings or the moons to get the maximum information. But that did mean they had to take a significant amount of fuel with them in order to give them that maneuverability once they arrived at their target. Let's look at the final section of this talk. What are these parking places that are called Lagrange points? What are they all about? Well, let's return to this picture I showed earlier and let's remind ourselves of the basic premise. The planet that is closest to the sun feels the stronger pull, and if it's the stronger pull, it moves faster and it has a shorter year. Greater distance from the sun, the gravitational pull is weaker, so the planet moves more slowly in order to stay in orbit, so it has a longer year. That's how planets go around the sun. But what about Lagrange points? Well, if we think about the red object being pulled towards the sun and the green object being pulled towards the sun, I've shown the yellow arrows there to show that they're being pulled towards the sun, and the size of the arrow reminds us that the green arrow is pulled more strongly, the green planet is pulled more strongly towards the sun than the red planet. Greater distance, less force. Okay, we know that Newton told us that gravitational force depends actually on the masses and the distance squared, but it doesn't really matter about the calculation, it's just the idea that matters here. So will this always be the case that an object further from the Sun will orbit more slowly? Well, we can't change the gravitational pull of the Sun, but we can arrange it so that the red object feels an additional gravitational force. In other words, what we can say is, let's imagine that the green object is the Earth, so that goes around the Sun in 1 year. The red object is in an orbit further from the Sun, so it has a period, you would expect, of more than 1 year. But what if the red orbit is not as indicated there, but is actually quite close to the green orbit? Not to scale this diagram, let's imagine that the red-green distance is actually quite small. If the red orbit is close enough to the Earth that the object is pulled by both the Sun and the Earth, then it feels an additional gravitational pull. The yellow arrow represents the pull of the Sun, the green arrow represents the pull of the Earth. And it is possible to calculate, we're not going to do it, but it's possible to calculate that there is a distance where the red object is at just the right distance from the Earth, such the extra pull of the Earth makes the red object orbit faster because of the additional gravitational pull. Remember, stronger gravity, faster motion. So instead of taking more than a year to go around the Sun, it's going to orbit in 1 year. In other words, the red object would orbit the Sun at the same rate that the green object orbits the Sun. So they go around the Sun lockstep. The red object is pulled towards the Sun and the green object, the Earth, is always on the same line. So this is not the way planets normally behave, but in this case it's a special case because the red object is close enough to the Earth. Let me just run that animation again. The red object is close enough to the Earth that the Earth provides an extra gravitational pull, which makes the red object go round in not a year and a bit, but a year. And hence the red object always seems to be on the opposite side from the Sun as seen from the Earth. The red object is always sitting there above midnight. Remember, of course, that noon on Earth is facing the Sun, so midnight on Earth is this point over here. So this point, this red object, is always sitting directly above midnight. And that's precisely what Lagrange points are all about. In this particular case, we've been describing L2. L2 is a point such that the pull of the Sun and the additional pull of the Earth means that L2 goes round the Sun in 1 year. Hence, as seen from our viewpoint on Earth, L2 seems to be a parking place. It's always sitting there on the opposite side from the Sun. Bear in mind that this picture is by no means to scale. The red object, the L2 point, has to be much closer to the Earth than indicated by my little cartoon here. The distance from the Sun to the Earth is 1 astronomical unit, and it turns out that the distance from L2 to the Earth is about 1/100th of that. It's about 1,000,000 miles or so, 1/100th of an AU. So this diagram quite definitely not to scale. I've exaggerated the distance to L2 just for clarity. And conceptually, it's exactly the same for L1. L1 is a point inside the orbit of the Earth where the Sun and the Earth pull in opposite directions. So the gravitational pull on L1 is less than simply the Sun's gravitational pull because the Earth is pulling in the opposite direction. So instead of having a period much shorter than a year, the period of L1 is exactly 1 year. So L1 is a great place to park a spacecraft. Again, where is it? Earth-Sun distance is 1 AU. L1 is approximately 1,000,000 miles, about 0.01 AU inside the Earth's orbit. And L1 is precisely where you would like to park a spacecraft. For instance, if you wanted to study the Sun, you would park a spacecraft there simply because the Earth never gets in the way. L1 will always sit between the Sun and the Earth and will go round with the Earth, and therefore you will have an unobstructed view of the Sun. Now, how do we calculate Lagrange points? Well, I've said that Newton told us how to do all of this. He basically said the gravitational force between two bodies is given by the mass of the two bodies and the square of the distance between them. And I'm sure you're quite happy with the idea that if we were to apply that to Lagrange points, we simply need to solve that equation. I assume you're all happy with that, yeah? Big M is the mass of the Sun, little m is the mass of the Earth, big R is the distance from the Earth to the Sun, little r is what we're trying to calculate, the distance from Earth to either L1 or L2. So all we have to do is solve for r. Simple. Well, okay, yeah, I did say in my splash screen, it's not that hard if you just skip the maths, so we're going to skip the maths. We just take it as read that somebody somewhere can do the calculations and work out where the Lagrange points are, where you need to be to park a spacecraft. It turns out there's 5 of them. I mentioned L1 and L2. I'm not going to go into more details, but there are in fact 5 points where you can park a spacecraft and the spacecraft will either stay put or stay fairly close to the particular point in space that we're talking about. And there are 5 Lagrange points for every object. Earth has 5 Lagrange points. Jupiter has 5 Lagrange points. Neptune has 5 Lagrange points. So the idea is, well, one option is to park at, for instance, L2. If you were to park a spacecraft at L2, remember L2 is always hovering above midnight. It's always 1,000,000 miles above midnight. And if you parked a spacecraft at L2, then a single sun shield can block the light from the Earth and the Moon and the Sun. If you were somewhere else in the solar system, you might want to block the light from the Sun and the Earth, but you would need 2 sun shields that were always in motion to do that. By parking at L2, a single sun shield will block everything and give you an uninterrupted view of the night sky on this side, because you're always looking away from the Sun and away from the Earth and away from the Moon. That's particularly important if you've got an infrared spacecraft doing infrared imaging or infrared spectroscopy, because you don't want the light and heat from the Sun and you don't want the heat from the Earth and the Moon to interfere with your experiments. Now actually L1 is in Earth's shadow, because if you work out that the distance from the Earth to L2 is about 1,000,000 miles, about 4 times further than the Moon. The Earth is about 4 times bigger than the Moon, so if it's possible for the Moon to cause eclipses, then the Earth eclipses the L2 point. So you don't necessarily want to sit at L2 because your solar panels won't work very well. So spacecraft like Gaia and the Webb telescope, for instance, they don't sit actually at L2, they do a little dance, a little orbit, a so-called halo orbit around L2. And that works because if you imagine drifting slightly away from the L2 point, if you were to move in this direction up or down, as indicated by my cursor, if the spacecraft moves away from L2, then the pull of the Earth naturally pulls it back towards L2. In other words, you don't need to use any fuel to stay there. It will always work to pull you towards that point. So that's why you can be in orbit around that point. The catch is it doesn't work this way. If you were to move towards the Earth or drift towards the Earth's pull will then get stronger, which pulls you more, which pulls you stronger, etc. So if you start drifting towards the Earth, then that's bad news. You do have to expend some fuel in order to stay at the right distance. If you were to drift away from the L2 point in this direction, again, you would continue to drift away from the Earth unless you had rocket motors to bring you back to L2. Now, one way of actually visualizing the ability to park at a Lagrange point is given by these sort of donut visualizations of what's going on. So imagine this donut is a set of contours, and the contours represent the height. Doesn't matter height above what, just think of it as height above sea level and think about a ball that wants to roll downhill. If we look more closely at what's going on around L2, so let's just blow that region up there, so we're going to ignore the rest and just look at the Earth and L2. The contours are high in the top left and they're high in the bottom left, and their contours are low around the Earth. But look at the contours around the L2 point there. The arrows show the directions of downhill. Notice that downhill is not continuously away from L2 and it's not continuously towards L2. 2 of the arrows point away from L2 and 2 of the arrows point towards L2. So this is a rather odd downhill map, if you like. L2 is not on the top of a hill as far as this contour plot is concerned. L2 is not in the bottom of a well, because depending on the direction you go, 2 directions are downhill and 2 directions are uphill. So L2 is actually at what is called a saddle point. Mathematicians would call it a saddle point because it looks like a saddle. If you imagine you're sitting at this point in the middle, then if you go this way, you go uphill. If you go this way, you go uphill. But if you go in the other 2 directions, you go downhill. So this is unlike a hilltop and unlike a well. So we can either call it a saddle point or we can call it a Pringle. Your choice. So the Webb telescope is sitting at a Pringle. It's actually orbiting a little bit around that particular point, but it can orbit because of this Pringle shape. But we do have to be careful, because if it drifts towards the Earth, we will need to give it a little bit of a station-keeping nudge every once in a while. This is why the Webb telescope has a finite lifetime. When it was launched, it was placed at the L2 point very precisely and used very little of its fuel, which means it now has plenty of fuel such that as it very slowly drifts towards Earth, it'll be given a nudge every few months or so to push it back to the L2 point. And because it is so precisely located with very little fuel used actually to get there, thanks to the Ariane rocket that got it there, so little fuel was used, it's got plenty in reserve to do these little station-keeping nudges every few months, and hopefully that will extend its life, not for just 5 years, but perhaps 10 years, 15 years, 20 years, possibly even more, because of its fuel reserves to keep it station-keeping at L2. So let's just very briefly think about the other Lagrange points, L4 and L5. Sometimes there are objects at L4 and L5. If we come back to our sort of donut picture, we realise that it is possible for objects to go into little orbits around L4 and L5, but Earth hasn't actually got a very strong gravitational pull, so it's very difficult for objects to collect at L4 and L5. But for larger gravitational bodies, for instance for Jupiter, then L4 and L5 can start collecting objects. And indeed there are Trojan asteroids in orbit at or close to the L4 and L5 points, being held there by the gravity of the Sun and by Jupiter's gravity. So they're not strictly at the L4 point, they are making small orbits around the L4 and L5 point. In principle, there ought to be objects in all planets' L4, L5 points, but you need a very strong gravity to hold, for instance, an asteroid there. It's possible there's just a little bit of dust at the L4 and L5 points of the Earth's orbit. One final thing with this particular diagram. Some orbits are really, really weird. We've seen that in principle you can orbit closely around L2 and L3 and L4, but actually you can do an orbit around any of these contours. And it looks really weird to think about an object that's following the red arrows here. And you think, how on earth can it orbit like that? You have to remember that this is not a static picture, it's a picture that's rotating as the Earth goes round the Sun. So it looks really weird, but it still obeys the basic rules. When the object is closer to the Sun, here for instance, closer to the Sun than the green line, which is the Earth's orbit, the object in this red orbit will go around the Sun faster than the Earth. The Earth is going around the Sun anti-clockwise, and so this object will move faster and will go round this curve here. When it gets closer to the Earth is going to give it a little bit of a tug and will tug it until it's the other side of the green line, which means it's further away from the Sun. But an object that's further away from the Sun will go more slowly. So again, this whole system is going around anti-clockwise, but because it's further from the Sun, this object will go slower than the Earth, and so as seen from the Earth, it will seem to go backwards along this line and come back to where we started from. So although it looks really weird, these sort of horseshoe-shaped orbits, they do obey the rules. Stronger gravity, they move faster. Weaker gravity, they move more slowly. And yes, they're not just hypothetical. It has been observed for instance, moons orbiting around close to the rings of Saturn. Objects have been observed to be moving in these horseshoe orbits. Perhaps the weirdest orbits of all are those that are not closed loops. I said very early on that when we're looking in the solar system, the orbits are circles or ellipses or possibly parabola or hyperbole. But it is possible for an orbit not to be a closed loop. Now, we have to set this up very carefully, but if you place three objects of equal mass at those three positions and don't move them and just let them go so that they attract each other under their mutual gravity, blue will be attracted to red and green, so that will start to move down. Red is going to be attracted to blue and green, so that's going to move to the right. Green is going to move to the left. What are you going to end up with? Well, the result is probably very surprising for most people. Let's watch what happens. That's probably the last thing you expected. And notice that they are now stopping and then they start to move backwards again. So this is not the same thing time reversed. That's the actual motion of these three objects if nothing else was influencing their motion. Is it possible for stars or three equal mass objects to do this? Well, it's almost impossible to set up because we would have to start with three objects at rest relative to each other, and then they would fall towards each other as indicated by these three rather weird looking orbits. But of course, when stars form, they never start their lives motionless relative to each other, and so it's effectively impossible to start a system in this sort of structure. And don't get me started on black holes. Black holes distort space and time so profoundly in the neighbourhood of the event horizon that you can't expect an object to orbit in anything even remotely similar to a circle or an ellipse or parabola or a hyperbola. Space is simply too distorted. So let's not go there. So I've been telling you about rocket science and orbits. Why have I got Kepler, Newton and Buzz Aldrin there? Well, Kepler observed the way planets move in orbits. Newton explained it, and Buzz Aldrin seemed to have an innate ability to understand orbits. His ability to work out orbital rendezvous was legendary. I've said a little bit about how you get from A to B, for instance, how you get to Mars and how you get to other planets. I then finished by saying a little bit about what Lagrange points are all about. The same set of rules applies. So why is rocket science considered to be so hard? Yes, there are indeed some objects in the solar system that move in ways that are not, at first sight, intuitive. And absolutely, yes, calculating how to put the Webb telescope into orbit around J2 was not trivial, especially given the phenomenal accuracy that ultimately they achieved. But the underlying idea is straightforward enough. The idea is, if you're in an environment where you've got a stronger gravitational pull, that leads to faster motion. Just think about the Earth moving around the Sun faster than Mars moves around the Sun. Everything else is just detail. That's really all there is to it. Stronger gravitational pull leads to faster motion. The rest is just maths. After all, it's not rocket science. Thank you for listening.